So today we are going to be learning a very new but also not new subject, which is integrals. So integrals means calculating area under the curve, and you've been doing this since day one of this class. You were estimating area under a curve with, when you were given a velocity curve and you were estimating displacement, that was area under the curve. So we're just kind of formalizing this now, but you have been working on this entire year so far. So let's say we have a function and we are trying to calculate the exact area. Now we know a bunch of different methods to estimate exact area. So let's say A is here and B is here. Okay, and I want to calculate the exact area from A to B. Well, we know that we can use, like we could start with like a left endpoint rectangle. We could use like a midpoint rectangle. Okay, we could have that. We could have a right endpoint rectangle. We could have any sort of rectangles. And we would use a Riemann sum to add up all of those rectangles. So in our Riemann sum, we're going to go ahead and start with n equals 0. And we're going to have k number of rectangles. Okay. So the width of each rectangle, of course, is our delta x. And then to find the heights, we had like delta x times n plus your starting value. But I'm going to go ahead and just say like f of x plus x to the first. Actually, x to the x sub n is what I'm going to call this. So we've got like our 0th rectangle, our first rectangle, our second rectangle, all the way until our kth, our last rectangle. Okay. So this is how we can represent it using kind of a Riemann sum. Now, in order to get a more exact area, because as you can see, this is not very exact, right? Think about how many rectangles I would actually want. I would actually want like a million tiny little rectangles. And then I would be a lot closer to the area, right? So what do we want k to be? We want k to be a very, very large number. In other words, we want the limit as k approaches infinity. Okay, so we want an infinite number of these rectangles. And then that way, if we have an infinite number, the width of each rectangle is very, very close to 0. So the width is really close to 0, but we're going to be so much closer to the actual area because we have so many rectangles. So our delta x is going to approach 0. So we have k approaching infinity, and then we're going to have delta x approaching 0. Well, instead of like writing this all out all the time, this is what we do. We write it as an integral. So an integral is going to be, it's going to have bounds. Our bounds are from a to b. So what that is the area from a to b. And then think about where this like Riemann sum came from, right? Delta x was the width, f of x sub n was the height. So this is what we do for an integral. We just switch them because, delta x times f of x is the same thing as f of x times delta x. So what I'm going to do is I'm just going to say, okay, well, it's the area under f of x. And then delta x is approaching 0. If delta x is approaching 0, what we do is we use dx to represent it. Okay. Now, why do we use dx instead of like writing out a delta symbol? So you recall that the slope between 2 points was delta y over delta x, right? So if I have 2 points on a function, I have point here, to calculate the slope between them, I do the change in y over the change in x. Well, what happened when we wanted to take the derivative? Well, we wanted those 2 points to be really, really close together, right? And so what we would say is the derivative is dy over dx. And that was the actual derivative, right? And that's when delta y and delta x are approaching 0. That's where this like notation of dy dx comes from. It just means your change in y and your change in x are both approaching 0. So dx here is the same thing. It represents your width approaching 0. Because again, if we have an infinite number of rectangles, then each one has to be infinitely thin. And again, this is the height of each rectangle, and this is the width. So people often get confused about like this dx here. A lot of students, like, they understand the f of x part, that's the function. They understand the a to b part, that's the bounds, but the dx, they always like kind of not always, but dx often gets left off or forgotten about or misunderstood. And so I just want to remind you, it's because we're adding up an infinite number of rectangles, and each rectangle has an area of a height times a width. If you don't multiply your height by your width, you haven't found area at all. So we do need to multiply by dx. That represents the width of each rectangle. Okay. So when you're looking at this example here, it says use geometry to calculate the integral from -1 to 3 of 2x dx. So again, the dx part just represents the width of each rectangle approaching 0. What's the height of each rectangle? 2x. So in this case, f of x is 2x. So the dx is there. It's a notational thing. It means it's our width. Our widths are approaching 0. F of x is going to be the 2x part. And then -1 to 3, 3 is our upper bound, and -1 is our lower bound. Okay. So when we're calculating this, what we're going to do is we are going to use a graph. It says use geometry. So geometry means like triangles, trapezoids, rectangles, etc. So it just depends on what this actually looks like. But we are calculating exact area. So when you see an integral, that's not an estimation. We're not using a Riemann sum unless it said in the instructions, use a Riemann sum to estimate the value of the integral. That would be one thing. But in this case, you're just given an integral. So we're going to calculate the exact area. And you just need a sketch of what this looks like. So 2x is just the line. It goes through the origin. It has a slope of 2. And we're going to go from -1 to 3. Okay. So the area from 0 to 3 is going to be this upper rectangle here. And the area from 0 to -1 is this lower rectangle here. And remember from our Riemann sums unit, if area is above the x-axis, we count it as a positive area. And if our area is below the x-axis, it is counted as a negative area. Okay. So what is our negative area here? So we have a width of 1 because we're going from -1 to 0. So that's a width of 1. And then what is our height? Our height, if you plug -1 into 2x, you get -2. Right? So our height is -2. And this is a triangle, so it's going to be 1/2 base times height. Okay. And then we're going to add our upper area, which is also going to be 1/2 base times height. Our base is going to be a base of 3. And then what's our height? Well, if I plug 3 in, I can find this point here. Plug 3 into 2x, I get 6. And then when I calculate these out, I get -2 over 2, which is -1, plus 18 over 2, which is 9. And my answer is an area of 8. Now, when you are writing out integrals and their answers, you do not need to write units squared. Even though that's what a definite integral calculates, it calculates the area under a function from blank to blank, but we do not write units squared. You can just write the number. Okay? So again, an integral represents the exact area under a curve or between the curve and the x-axis from a lower bound to an upper bound.